Okay, so this class is on paired t-tests, and I'm going to start off by just giving you kind of a quick example of what a paired t-test is and the sort of data that we're going to have. So imagine that we were in a classroom situation, and I was actually a nice person. I brought you a load of chips to eat, and we've got two different types of chip. So I'm going to write here paired. And here I'm going to write kind of independent samples. So in the paired t-test, what we would have is we would have, for example, let's just say we have our two brands of chip. We have prawn cocktail, PC, and then we're going to have Worcester sauce, WS. And the key here is, let me just write a little diff here. Each person in this case in the class, or from a sample of students. So I'm going to draw some people here, but you get the idea that these are separate people. You don't have to put up with my bad art skills to know that. And so say, for example, the first person, prawn cocktail is obviously the best flavor of crisps. Chips, we're going to go from 1 to 10. This is going to be a 9, and this is going to be a 7, and the diff is going to be 2. Then we're going to have 8, 8, 0, 6, 5, 1. And then this person doesn't know what's happening, so they make a bad decision and they prefer Worcester sauce. And then maybe this is 3, 2, 1, and then 1. This person just doesn't like these chips, then that's a 0. And the idea here is we're reducing variation in the data by comparing across, it's one person. So we have, we're controlling for a certain amount of error. Independent samples would be a little bit different in that we would actually have separate samples of people. So maybe we would have a sample of, let's just make this, n equals 10. And we've already kind of covered this, n2 equals 10. And so we'd sample 10 people to have prawn cocktail crisps, etc. And 10 people to have Worcester sauce. Etc. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we've got 2 more down here. You get the idea, we have 10 in each. And there's a degree of independence here. There's no linkage between this 9 and 8. The 9 is sampling somebody, the 8 is sampling somebody. Just to kind of give you one more example, let's just move this across. Yep. I think we need the hand. And this might actually be a better example. Imagine that we are playing golf, and we've got 2 different brands of golf ball, kind of A and B, and we want to compare how far they go. And we've got somebody, I don't really kind of keep up with who's good at golf, but maybe they have Rory McIlroy, and he hits A 290 yards and B 260 yards. And then we have Tiger Woods. He used to be good, but maybe he's not quite as good anymore. And then we'd have me, and I just hack things around, and I'm 106. I can't really play golf, 170, etc., etc. Now, and then there's somebody even worse than me. So there's, just call this worst person, and 140 and 135. And you can see here that there's a great deal of variation here. So if we were to do this as like an independent sample test and randomly pick 10 people, they try golf ball A, randomly pick 10 people, they try golf ball B, there would be a lot of variation due to the competency of the golfer. So it's going to be hard to get a significant result. If you've got people hacking around with around 100 yards and people shooting 300 yards, compared to any difference between the brands, there's going to be a high standard deviation, and the kind of the independent samples test that you did in the previous chapter wouldn't work particularly well. But with kind of paired samples, we're going to be working on the differences. And -5, -10, higher, it's going to be 5, etc. So we have much less variation. So because the difference between me and Rory McIlroy, this 130 yards, is not actually considered part of the variance of the test. It's almost been taken out by the experimental design. Okay, so that's our little kind of idea. So what we're going to do is I just gave you an idea of why we use paired designs. We're going to talk, this was kind of where you have a single person or a single item. That's probably the easiest type of paired design. We'll also talk a little bit more about match designs later in the chapter. We'll also talk a little bit about the about confidence intervals and hypothesis testing. Okay, so a few things, and I'm not going to write. I'm just going to kind of annotate the slides today. I'm not going to, since I don't have a board. But this is the confidence interval. Now, the key here is when we were defining before, so let's just do a simple example that we have maybe groups A and groups B. And then we have the diff. And let's just say this is out of 10. So we have 10, 8, diff is 2. Not quite sure what's going on to the left here. 7, 7, 0, 9, 8, 1, 7, 9, -2. I was going a bit low. And then we have an n equals 4. So the difference here, we'd have x bar d would be equal to 2 plus 1 is 3 minus 2 is 1 divided by 4. You get the idea. And then we could also calculate, and I'm not going to do it, we could also calculate the standard deviation on these differences. Okay, so that would be like 2 minus a quarter, 0 minus a quarter, 1, etc., etc. So we could also calculate the SD on these differences. Not quite sure what's happening with all these lines here, but let's just roll with it. So we work on the differences, and this is very similar to the single sample test. We could almost kind of cross out the D's, and this would be over root n, which would be approximately equal to x bar plus or minus z alpha over 2 s over root n. Okay, so let's just kind of have a look. We're going to do the confidence intervals. Key thing here is this is just a confidence interval for mu1 minus mu2. So for example, this would be the, the mean for prawn cocktail minus the mean of Worcester sauce. So it's really, in terms of how we set this up in what we're testing, it's similar to the independent samples. But in terms of implementation, it's more like um, a single sample test. For example, if we were to say just, scratch out these D's, we would just have a single sample test. So the key thing here, some key points, it's, we're calculating, we're making inference on mu1 minus mu2. So just like the independent samples tests, but all our calculations are exactly the single sample test but on the differences. For example, if we were to go back to the examples I started with, let's keep my indentations for the moment. You can see that we've calculated the differences. So here, let's just have a look at this first example. Here we would have, our ND or our N would be 1, 2, 3, 4, 5, 6. And our X bar D would be 2, 3, minus 6 would be minus 3, minus 2 would be minus 2 over 6 equals minus 1 over third. I'm not going to calculate SD, but it would literally just be calculating a sample standard deviation on those particular differences. So it's very similar for the single sample tests. So again, we calculate, the setup is exactly the same as, for a two sample independent samples test. We could almost, and as I said, we're really not going to encounter many situations where we have this D0 value, where we're saying the difference between the means is 3 or 4. In most academic research, we're comparing two groups. We're comparing two groups of consumers. We're comparing managers in family businesses versus non-family businesses. So, this would be exactly like, mu1 minus mu2 equals 0. Mu1 minus mu2 is less than 0 or kind of greater than 0. And this would be exactly the same as the independent samples test. Yep, sorry, mu1 minus mu2 is not equal to mu0. But we are basically doing the same calculations as for a single sample test. And let's just remind, I didn't mention this before, that if we were doing a t-test, we have, and this is important, we have n minus 1 degrees of freedom. So the degrees of freedom are as per the single sample test. We literally are doing a single sample test on the differences. So let's go a little bit further down. So the hypothesis test, we don't, it's kind of self-explanatory. This is for the equivalent of a single sample Z test. So, we'd have like Z equals X bar, and we don't really worry about the D0, sigma D all over root ND. And as we don't really know the population standard deviation, we always usually estimate it with the with the S. And then the small sample is equivalent. And again, exactly the same as the single sample test. But the key is, again, we have n minus 1 degrees of freedom. So again, the x bar d divided by s over root nd. And rejection regions are exactly the same as for the single sample test. So rejection regions. Single sample. Z, comma D test. Okay, so we've kind of got, we'll talk a little bit about the conditions. So again, we're doing this kind of equivalent of a single sample test. So this is exactly the same conditions as a single sample test. So for a Z test, we're basically taking a random sample from the population of differences. And my ND needs to be large for the central limit theorem to kick in. And we assume that the sampling distribution is approximately normal. For the Z-test, it's very similar. So for Z-test, so for a T-test, you know, 1 is as above. But 2 is basically, you know, either ND is large, so the T so T is kind of going to the Z distribution, or, you know, ND is small and the underlying data are approximately normal. If we have a small sample and our differences are not normal, understand underlying data distribution for differences. Sorry, I'm off the edge of my tablet here. So very, very similar again to the single sample T and Z test. So if ND is less than or equal to 30 and not normal, so I've not got room, but say and not normal, then we'll use non-parametric tests, which we will cover in this course later on. And we just kind of did that. So random sample. And again, most people in practice will use the t-test with large samples, regardless of whether the data is normal or not. Okay, so here's a little example. And it's almost like a little trick question. I don't know if I would actually be nasty enough to do this trick question in the exams, but okay, so we have a weight loss program for adolescents. So they're basically, I guess, overweight. So we send them to a camp. We've got 76 individuals, so N is large. So in this class, you can use the T or the Z, but, basic stats textbooks will do this as a Z test. Now, interestingly, this is where it becomes almost a trick. We are measuring for the individual. So this is a paired. Each individual, we measure their weight before and after. So it's a paired test. We measure it before the camp and after the camp. And we have the before mean and standard deviation and the end mean and standard deviation. Because the data are paired, they're not independent. To do a two-sample test, so do a two-sample independent samples on this data, that would be wrong. I'm just going to put wrong and like triple exclamation points there. But we do have, they've given us the differences. So as I said, we always work in the differences. So we have the mean differences and the standard deviation of the differences. So we actually have our X bar D is 3.3, our SD is 1.5, and my ND equals 76. Be sure when I set the extra questions on the homework, you will really see if I set one of these questions in your exam, I really emphasize something like paired or differences, and some people still try and do it as an independent samples test. Okay, so here's, and again, I've got this here, so unlike class, I won't write this out. So we're going to do a 99% confidence interval. So our alpha equals 0.01 and alpha over 2 equals 0.005. That's one of our standard z's from our normal table, so that's 2.576. Again, plus or minus z alpha over 2, 2.576. SD, 1.5 for the previous slide. Square root of n, square root 76. This is our XD. Now note the mean difference. This is before minus after. So we're thinking in terms of weight loss. If we do I mean, we could do it the other way around. There's nothing to stop us, but mu1 minus mu2. The first column is before, the second column is after. If we lose weight, so this is mu1 is higher than mu2, this would be a positive. So this would be the actual weight lost rather than the, so this person would say we had a single person where they were 80, and then they lost 5 kilograms and they were 75, then they would lose 5 kilograms. The distance for this would be, sorry, the difference, not the distance, would be 5. So we usually do for confidence intervals. We calculate the half width, the margin of, the margin of error. We add and subtract to the mean, and then we get the overall range for the confidence interval. So the 99% confidence interval is going to be from 2.857 to 3.743. And this is the time in the class I ask you, I will shout out, what about a 95% confidence interval? Is that wider or narrower? And you would say it's narrower because we're less confident. This is the range of confidence for this difference in means. And also just the z table, that would be a 1.96. Okay, so this one, and again, I try not to trick you. If I do a one tail, greater is kind of telling me that I want to be, greater than, we're doing a greater than test, but starting greater than end, which is start minus end, which is our difference. So again, we're doing this on the difference, which is start minus end. Our mu d is 0, and we could easily write, if you were to write in the exam for this, if you do mu d, I'd kind of want you to define mu d, but you could easily just write, and I would not grade that incorrectly. Okay, and again, the test statistic, you can or cannot include the 0 because we don't really do with the D0. The rejection region, we're going to do alpha equals 0.01. And again, the standard values from the table, this is going to be z is greater than 2.33, one of our standard values. And we do the calculations. And obviously this, we've got 3.3 is our mean, which is much bigger than the standard deviation. Now the key here is this whopping sample size. So this is going to have what we talked about with our effect size a couple of weeks back. This is obviously going to really inflate the z-value. So the z-value is 19.179. Just kind of think about our rejection region. And I seem to lose my pen. Yeah. Let's just do that. And put that in the middle. And then z alpha equals 2.33. And then we're kind of way out here. Just to show I'm not lying, let's just go to the statistical table. So we have beyond z, 0.01, around 2.33, and our 19 is going to be way, way off. It's going to be 0.000000 or something like that. And again, if we go to the effect size, the effect size agrees it's a very large effect size. We've got the combination of a very large effect size and, at least for the type of things we do in this book with small data sets, quite a large sample size, which is why we've got this absolutely ginormous t statistic. Okay, so that's about it. We're going to kind of resume on the second video. We're going to talk about paired difference experiments in general. We're going to talk about type of design, and then we'll give another example, this time of a match design with data in Microsoft Excel.